Okay, have you ever wondered what objects would look like in 4 dimensions?
No. Oh wait, yeah. I've always
Okay,
I them.
yeah. So the bad news is you'll never know because you don't have access to a 4th dimension to know, and you could never, I could try to explain it to you, but if I did, I'd be lying because I don't know either. But there are some things you can kind of start to get a little bit of insight into what a 4D universe would be like, though, just a little bit. So let's to do that, to get an idea of what 4 dimensions, how that would differ from 3 dimensions, best thing to do would be to maybe let's use some analogies in dimensionalities we do understand well. For example, if I wanted to take, how many dimensions are required to create a cube? A cube resides in how many dimensions? 3. Yeah, 3, right? We need all 3 dimensions to create a cube. What's the net of a cube?
The net?
Mm-hmm. Okay, good. So it's this thing, right? It's like if I took a cube, if I took just the surface of a cube and I unfolded it to create a 2-dimensional shape, right? That would be a net. Okay, so the net of a 3-dimensional object is 2-dimensional, and this would be examples of different nets of a cube. There's a bunch of different ones that would work. Here's 4 different examples. Each one of those, would you agree, if I folded on the lines, would fold up into a cube, right? And here's folding instructions for one of those, okay? If you want to see it in action, here's an unfolding and refolding net of a cube. Okay, get the idea? Okay. So I want you to kind of just think here, extrapolate a little bit. So if it's true that the dimension, or the dimensionality of the net of a 3-dimensional object is 2, right? If you unfold a cube into its net, it's 2 dimensions, right? Because the surface are all pieces that are 2-dimensional pieces that we stitch together to create the 3-dimensional surface. What do you think the net of a 2-dimensional object would end up being like? How many, it would be 1-dimensional, right? And here's an example, like if I did the net of I actually forgot a piece there, didn't I? If I did the net of a square, which is 2-dimensional, if I unfolded all 4 of those line segments, they would just create that. It's pretty boring, right? Anybody see that? It's a 1-dimensional object because it exists on a single line, and that would be my 1D net of a 2-dimensional square. Okay, then even though we can't visualize things in 4 dimensions because we don't have access to that extra dimension, it doesn't exist in our 3-dimensional universe, we could draw a conclusion that's kind of interesting here. If I were to take a tesseract or a hypercube, whatever you want to call it, a 4-dimensional cube, and I were to unfold that into its net, how many dimensions should the net have? Should have 3. Yeah, so we could see what the net of a hypercube would look like. That we can visualize. And it would look like that. That's the net of a hypercube. Okay? So all you've got to do now is just fold that up into 4 dimensions to see what the hypercube looks like. Only problem is we can't do that, right? Now there are, you can do some hokey things that kind of give you a hint of what the behavior would be like by using maybe shadows or projections. Like if I were to do, how many dimensions, if I take a 3-dimensional object and I project it onto a surface, how many dimensions is the shadow or the projection? 2, okay? So we could do something similar. If I were to project a hypercube into 3 dimensions, we could kind of see what its shadow looked like, and this is what we would find. Something kind of like if we were going to start, this is sort of what I'm going to do here on this page. This is pretty cool. It's going to start with 0 dimensions, which is a point, and we're just going to keep adding dimensions at right angles to the previous parts of the drawing, right? So it starts with 0 dimensions, goes to 1 dimension, which would be a line segment. Then we're going to put those cards away. What do we got going there with? What's that? No, you can't have those out. Those have to be away. Like seriously, like I'm gonna tell you one time for the rest of the year, or those are mine. Those have to be away. So, you know, and then we'll draw another dimension perpendicular to that one dimension, which would create a square and so on. And it just looks like this. So there's 0 dimensions, there's 1 dimension, it's a line segment. 2 dimensions is a square. 3 dimensions is a cube. We're all good up to there. Now it kind of gets a little crazy. Now we'd have to look at the projection of a tesseract or hypercube, which would look kind of like that. That's what its shadow would sort of look like. Okay, it'd be a little strange. It's projection. So this would be one way of kind of trying to visualize what an unfolding and refolding hypercube would be. But again, it's pretty hokey because you can't actually see what a hypercube would be like. Another thing you could do is you could take the shadow, like if I were going to rotate a cube about something, I'd have to rotate it about a line, right? That would make sense. I could take this axis right here, for example, and I could rotate this cube about that line, and we could visualize that pretty easily, right? And we could even see what the projection would look like in 2 dimensions if I did that. You know, we could kind of get a cartoon of what that would look like that would make sense to us, okay? If I wanted to rotate a hypercube around now if I rotated a square, I would be rotating it about a point. And then that square would just be kind of rotating around that point in the board. Again, we could visualize that easily, right? If I wanted to rotate a hypercube, I would be rotating it about a plane, which would make no sense to us, but that's the way you would do it. You'd rotate it about a plane, and this is what the projection would look like in 3 dimensions. So again, very, very bizarre. Okay? And here, if I did a double rotation about 2 orthogonal planes, 2 planes at right angles to each other, you'd see something like that. That's what the projection would be. Very bizarre. Okay. So again, that's probably not very satisfying, but we could maybe get a little bit better insight into this if I could introduce you to some friends here. I haven't told you about this, but the board that I use up here is actually, it's a flat little universe called Flatland. It's inhabited by creatures. This is Mrs. Red and that's Mr. Blue, or Miss Red and Mr. Blue. They reside in this flatland and they move around. They know each other, right? They move around in this flat universe up here and they play games and have fun and they learn flat math and do all kinds of good stuff. Okay, so let's investigate their lives a little bit, and by knowing how we interact with them, that would predict how a 4-dimensional creature would interact with our 3-dimensional universe, right? So let's first of all think about how we interact with our universe. Like when we see things visually, the visual information we take in contains how many dimensions of information actually? Like we see things in what D? No, we don't see things in 3D. Because if we did, I could see something that is behind a person and I can't. We see things in 2D. We stitch together a series of 2-dimensional pictures on the back of our eyes. Our brain does that. And we can use that information, we can stitch it together in time and create like a frame of videos that allows us to understand or conceive of our 3-dimensional universe, even though we actually only perceive it in 2D. Now, we have stereoscopic vision, which helps, right? But there's some other things that happen that really, that give me some visual cues. Like if I walk along the front of the room, people in the front row are moving by my field of vision faster than people in the back row, which my brain immediately interprets as, oh, they're closer, right? Things that are further away are smaller. And so that's another visual cue. And so I can understand, I can conceive of this idea of frontness and backness, even though I don't get that information directly from the pictures that my brain is capturing, right, from my eyes, that are transmitted to my brain from my eyes. You can trick people pretty easily because our brain is pretty good. We've developed all these cues that we use to interpret how far away something is. But like if you've ever been to one of these fun houses, where the dimensions of the room are real crazy, you can have a person sit in one corner and they look enormous because the lines of the room make it look like that corner is far away because they recede into the distance kind of. but in effect, they're not. Like you could have a place in the room that's actually close to you, but because of the way the structure of the room is built, it looks like it's far away. So if you sit in that spot, you look really big, right? Have you ever been in one of those, have you ever seen something like that before? Just optical illusions. I mean, it's really easy to trick your brain because we rely so heavily on these visual cues. Okay, well then let's extrapolate here. We live in a three-dimensional universe, but we perceive it in two dimensions. So the Flatlanders live in a how many dimensional universe? Two, right? Two-dimensional plane. They see or perceive their universe in how many D? One, yeah. Now, can we kind of wrap our heads around that? Not completely. We could never really experience what they experience because we don't live in a flat universe. We live in a three-dimensional universe, right? But maybe you could think, okay, well, one way we could do this, if I just kind of stuck my head into Flatland, what would I see? Well, what would their universe look like to me if I did that? If I kind of just, put my head into their universe far enough that my eyes were lined up so I'm in their universe, what would it look like to me? Okay, it sort of looked like maybe just a white line, right? And everything else would be like the room, but let's pretend the room's, I've turned the lights off so it's really dark, right? So I just see blackness below and above, and I just see this white line that's their universe. And what would the individual creatures look like to me? What would Mr. Blue look like? Just a little blue line segment, right? And I could see that as he gets further away, that gets smaller. As he gets closer, it gets bigger. And so they have the same information. They're smart. They understand about being far away. They understand about, if he walks around, like let's just say that, here's, there's Mr. Green, and Mr. Blue sees that if he walks around, right now he can't see Mr. Green, he's obscured, but if he walks this way, oh, now he can see him. So he was just behind Miss Red, right? And so they have the same kind of understanding of their universe that we do. But that's really an incomplete understanding for us because that's not how they would see it. Right? When we interact with their universe, we get this white line that's embedded in this otherness, right? We get this other black place above and below it. They don't have that. That's not even in their vocabulary, right? They wouldn't even understand what we're talking about if we said, oh, your universe is a line, and everything that's below it or above it is black. Well, they would think like, below or above, what are those words? Those aren't in our flat dictionaries. We don't know what those are, right? They don't get that. To them, that's everything. And so we could never completely even understand how they see their universe, right? How would we, if we interacted with them, they would see us as pretty bizarre creatures. Like if I stuck my hand into the universe, they would see, if I put my finger in there, they would see, oh, this little line segment. And as I go further in there, it's going to get bigger, right? And it kind of changes. You might think, okay, well, we could explain to them what that is if they just took little flat pictures with their flat cameras. And I say, okay, here I am. Now I'm going to go a little further in there, take another picture and another picture and another picture. They could stack those up and create an image of us, right? What's the problem with that logic? They don't know. They can't stack them up. How are they going to stack them up? They have no way to stack them up. They don't have that extra dimension to stack them up, right? You get my point? So they could never really have any idea what we looked like. They couldn't understand what anything in our universe looked like because they're relegated to these two dimensions and that's it. They have no frame of reference to understand another one, right? Okay, do you see that that's the way it would be for us with higher dimensional creatures? If they interacted with our universe, we would just see the three-dimensional intersection of them with our universe, but we could never like stack those together in some way to understand what the four-dimensional creature looked like. Or it doesn't have to be a creature, an object, right? You see my point? Okay. This is bizarre. Are you thinking, why are we studying this? Why are we talking about this? Well, there are some practical reasons. First of all, even though our universe only has three dimensions, I'll give you a couple reasons that this might be interesting. Well, for one thing, cosmologists now sort of are leaning towards the idea that our universe is just one that's embedded in what's called a multiverse. It's this inflaton field, and our universe is a little bubble in the inflaton field that where the expansion was interrupted, and so we're stuck in our universe, and the properties of our universe are frozen in place as a part of our universe. But there could be other bubble universes outside of ours that are completely different, that have different physical characteristics. They could have 4 extended dimensions and 2 time dimensions. They might have 2 dimensions and no time. I mean, there could be all kinds of weird things, right? That's speculative. I mean, we can't interact with those universes, and so that really doesn't matter that much. But even in our universe, understanding this kind of interactions of dimensionalities is important, and I'll give you a reason why. What happens if I drop this eraser? That's magic. It fell. There's nothing attached to this, right? There's no strings, and yet this thing fell. Why? Gravity. Okay, you got that. I mean, what's gravity? It's an attraction. It's a force, right? You might even, if you study physics, you'll learn the word force. You've heard the word force, obviously. So forces act between objects. So what are the objects that are attracting each other here to make that thing fall? The eraser and the Earth. Yeah, okay. So the mass of the Earth and the mass of the eraser create this gravitational field, and they're attracted. If you really, okay, now really focus here, okay? Close your eyes and really focus. I'm going to tell you when I drop the eraser and see if you feel it. Okay, ready? I'm going to drop it on the count of 3. 1, 2, 3. Did you feel the Earth rush up a little bit to meet the eraser? Because it did, a little bit. When I dropped this, the center of mass of the eraser and the center of mass of the Earth both came together to some common point. But the Earth didn't move very much because a mass of 6 times 10 to the 34 kilograms is a lot bigger than this little eraser. And so it didn't really move very far. But it did move a little bit, right? You probably didn't feel it. But it did. Okay, well, that explains it. It's that force. But why? I mean, just calling it a force and even applying equations to it doesn't really explain why it happened or how it happened. It just predicts that it did happen, and we have a math model to precisely predict how long it's going to take for this thing to hit the table, or what its speed will be when it hits the table. You know, the mechanics you learn in Mr. Cooper's class will tell you that, but they don't tell you why. Does anybody know why the eraser actually falls to the table? Why it accelerates towards the table? Einstein explained this to us over 100 years ago. What did he tell us? For the first time, he actually explained why gravity works, what it really is, why the equations that we'd been using prior to that were pretty accurate but not perfect. What's really happening, and this is the honest truth, if I drop this eraser, it's falling into a higher dimensional gravity well. The fabric of the universe is actually warped by the presence of massive objects, and it's warped into this extra dimension that we can't see, but we can experience its effects, right? We can't see the well that it's falling into, but we experience that as it falls into the well, it accelerates, okay? Well, this is pertinent then, right? Because this is understanding this idea of, just if we extrapolated from 3 to 4 dimensions, what would the effects be? Well, that's one of them. One of them is that, it would cause gravity, okay? There's some other pretty bizarre things too that you could take from this. Like, let's just say it turns out that Miss Red and Mr. Blue are dating, and he's gotten her a present, gotten her this beautiful star-shaped pendant that he's wrapped in this nice little green decorative box. She can't see it. It's inside the box. He already put it in the box and sealed it, right? She's going to be very surprised. He can't see it, but we can. Without him even opening the box, we can see. How come? Because we have an extra vantage point that these guys don't have, right? We can look down on this from this extra dimension that they don't have access to. So what are the implications there? Do you guys know what's in this box? No, because I put it there before class. But a 4-dimensional student who's sitting listening to some crazy 4-dimensional teacher talk about 5 dimensions, I don't know, they could be looking down on us right now, and they would know what's in that box because they're looking they have the extra benefit of being able to see from the perspective of another dimension outside of the 3 that we have, and they could tell that inside this box is a pack of gum. They would have known that before I even opened it. How crazy is that? Crazy, crazy stuff. Anyway, 4 dimensions, there it is. Did my little spiel. There won't be an assignment on that, but I just wanted you to get a sense of, it's kind of interesting if we're talking about dimensionality and extending, you know, to 3 dimensions. What happens if you take it a step further? That's what happens. Oh, I'll let you work on this assignment, but real quick, I guess one thing it might be worth doing is taking 15 seconds and just reminding ourselves how we solve 3x3 systems algebraically, right? What was our strategy? We have to use elimination. And what's our strategy here? What do we have to do to this 3x3 system?
Make it 2 by 2.
Yeah, we got to make it a 2x2, right? We have to use 2 different pairs of equations, eliminate the same variable from 2 different pairs of equations to create a 2x2 system. So think what we did in this example, right? We took the top 2, we decided it was easiest to eliminate y's, right? We could do that by multiplying the middle equation by 6 and leaving the top one alone and adding those together. I eliminate the y's. Or by multiplying the bottom equation by -1 and combining it with the middle equation. I eliminate the y's. And those 2 equations that I get, when I do that, both of the 2 equations lack a y, and so that now becomes a 2x2 system that I can solve the way I solve 2x2 systems, right? Just, it's a smaller problem contained in the bigger problem. I just solve this 2x2 system by using elimination, and I get z equals 4. I plug that back in to find the value of x. So solving that 2x2 system, we find that x is -1 and z is 4. And then to find the third variable, all I have to do is pick one of those equations and plug both values back into that to find the other missing variable, which was y in this case. Okay? Make sense? I'm not going to bother you. I mean, we already did a bunch of examples, so I'm going to let you guys work, but I just wanted to quickly remind you how that all goes. All right, jump in, get some work done.